So we are going to be dealing with section 5.1, day 1. And you should have printed out, or at least be looking at this worksheet on your computer from Angel. It's on the worksheet, in the worksheet folder on Angel, because it's a little hard to see up here, so it'd be better if you had it to look at as we're going through it. So the first thing that we're going to talk about in section 5.1, day 1, is the idea of number theory, what we mean when we say number theory. And it is a branch of mathematics that's devoted to the study of just the counting numbers. So we wouldn't include 0 in that, because 0 is not a counting number, it's a whole number. It's an integer, but it's not a counting number. So we're just considering the numbers 1, 2, 3, 4, and so on. And with number theory, there are two definitions you need to know. One is what a prime number is, and the other is what a composite number is. So a prime number is defined to be a counting number with exactly 2 factors. And some examples of prime numbers are the number 2, because its factors are 1 and 2, and that's it. There aren't any other ones. Another prime number is the number 3. Its factors are 1 and 3, and that's it. We wouldn't say 4, because 4 has factors of 1 and 4, and it has a factor of 2. So I guess I better back up a little bit and make sure we understand what the word factor means. Factors are, the factors of a number are 2 numbers that multiply to make the number in question. So if you think about the number 10, you can think of 1 times 10 being 10, but 2 times 5 is also 10. So there are more factors there than just 2. So another way to think about a prime number is if you can only write it as a multiplication problem using the number 1, then it's a prime number. So for example, the number 7, the only way to write that as a multiplication problem is 1 times 7. It's prime. So you could go, any number that you think about, you could say, is there another way to write it other than 1 times the number? If so, it's not prime. If it's not prime, it's composite. So that number 4 that we talked about is composite, because not only can I write it as 1 times 4, I can also write it as 2 times 2, which means 2 is a factor of 4. So the 4 has factors of 1, 4, and 2. As soon as I get beyond exactly 2 factors, now it's composite. So the number 24, I can write that as 1 times 4. I can write that as 2 times 12. I can write that as 4 times 6, 3 times 8. There's a lot of ways to write that as a multiplication problem, which means it is a composite number. It has more than 2 factors, more than just, oops, this should have been 24, more than just 1 times 24. So composite numbers are counting numbers with more than 2 factors. So that leads us to the big question, what about the number 1? Well, to be a prime number, it has to be a counting number, which it is, with exactly 2 factors, but it doesn't have 2 factors. The only way to write 1 is 1 times 1. That's not 2 different factors, that's the same factor twice. So 1 is not prime, 1 is not composite. So the number 1 is the only counting number that you can't put into one of those 2 categories. You can't call it prime, you can't call it composite. It is the exception to the rule. It's not one of those 2. Any other counting number, you should be able to put it into one of the 2 categories. It's prime or it's composite, but not the number 1. So moving on from those definitions to the idea of a factor tree. A factor tree is one way to write a number in what we call prime factorization. to be prime factorization, you have to take the factor and break it into other take the number and break it into factors and keep going until you get to the prime numbers. And so the reason why it's called a factor tree is you sort of branch out. And you can branch out any different way you want. You could decide to break this into 2 times 30. You could break it into 6 times 10. You could break it into 3 times 20. Any two numbers that you can think of that multiply to 60 can be your first step. So I'm going to take my first step with 6 times 10. But 6 and 10 are both composite numbers. 6 can be written 6 times 1, but it can also be written 3 times 2. So it's not a prime number yet. So I'll break it down then into 2 times 3. Now I've hit my prime numbers. Because if I want to break down 2, my only choice is 2 times 1. And as soon as you get to that point where your only choice is the number times 1, you stop. This is prime. 3 is the same thing. It's prime. Stop. 10 is not prime. It's composite. So we're going to break that down into 2 times 5. 2 is prime. 5 is prime. That's where I stop. It doesn't matter if you started with 6 and 10 or you started with 3 and 20. However you started, you should end up with these same 4 numbers at the end of your tree. So let's just check that out and make sure it's true. We'll break 60 down into 3 times 20. I would stop at 3 because that's prime. But I'd have to keep going on 20, maybe 4 times 5. I would stop at 5 because that's prime. But 4 is not, so I'd have to keep going to 2 and 2. So whichever way I decided to do my tree, the numbers that I underlined are my prime factors. 2, 3, 2, 5. 3, 2, 2, 5. They're the same numbers. It doesn't matter what order they're in. They are the prime factorization. But the way you're going to write it is you're going to take each of those prime factors and tell me how many times they happen. The number 2 occurs twice. So you want to write it as 2 squared. We're using an exponent to say I have a 2 and I have another 2. Times 3 is my other factor, and 5 is my 4th factor. So I have a 2, a 2, a 3, and a 5. But I'm going to use this notation to express how many times 2 is a factor. And factor means multiply, so I'm putting dots between them to indicate if you multiply 2 times 2 times 3 times 5, you would get 60. But this is the prime factorization. So if we do the same thing with the number 84, we could break 84 down into 4 times 21. We would have to keep going on both because they're composite. 2 times 2, 3 times 7. They are all prime numbers because I'd have to do 2 times 1. That'd be the only way to break this down. 3 times 1, 7 times 1. So I stop. My prime factors are 2, 2, 3, and 7. I would write it as 2 squared times 3 times 7. That's the prime factorization of 84. And you can check yourself, multiply them all up, and get 84. And make sure none of them are composite. Make sure you went all the way down to the prime numbers. So factor trees are important. The idea of writing in prime factorization is very important as your students move on to math. And factor tree is one of the ways to see that. So there is a fundamental theorem of arithmetic that you should know. And it says that every composite number can be written as the product of prime numbers in exactly one way. In other words, if you make a factor tree and your neighbor makes a factor tree, your factor trees should turn out exactly the same way. if you've taken it all the way down to the prime numbers, the order of the factors might be different from yours and your neighbors, but it doesn't matter because there's a property in mathematics that you should know called the commutative property. And in case you don't know, the commutative property looks like this. It says that if you take a number and you multiply by another number, it doesn't matter what order you do that in. You're going to get the same thing. So A times B is the same as B times A. 10 times 7 is the same thing as 7 times 10. And so when you do your factor trees, it doesn't matter what order those factors come out in. And in fact, a lot of times what we like to do is put them in order smallest to largest, because it's easier to compare. But you don't have to. Like, I could have taken my factor tree of 60 and written it in prime factorization like that. It's the prime factorization. It's the same as what I have up top. It's just a different order. But to be consistent and so we can compare with other people, a lot of times we just like to put them in order, smallest to largest. And but I couldn't mark it wrong if you decided to write the prime factorization of 84 as 7 times 3 times 2 squared. Because if I marked it wrong, you could say, wait a minute, the commutative property says that it doesn't matter what order I put it in. And that's true. So that's the fundamental theorem of arithmetic. And in basic terms, you could think, I make a factor tree, Joe makes a factor tree, Karen makes a factor tree. We should all get the same thing in the end, as long as we didn't stop before we got to the prime numbers. So flip into this back side of the page. There is more vocabulary that you need to know and notation that you need to know. So I tried to take from the book and just copy it and paste it into this worksheet so that it's in a nice, concise way. The first vocabulary word you need to know is underlined there at the top. It's divides. So the definition of divides is that if A divides B, and the way you write that is with a vertical line, A vertical line B. A divides B if and only if. These are really important words in math. If and only if. It means that the only way that it's true is if there is a whole number x. So there is a number out there somewhere, and the x is such that the A from the beginning times the x equals the B. So looking at this example and trying to take those words and figure out what they mean, 3 divides 6 if and only if you can think of a number, x, such that 3 times that number equals 6. So because we know that 3 times 2 equals 6, we know this is a true statement. 3 divides 6, that's true because 3 times 2 is 6. So this x, the number x that I'm, put it wrong place, sorry. The number x that I'm talking about is that number 2. Because I can think of a number that I multiply 3 by and I get 6, 3 divides 6. So using that same logic, 3 divides 9, 3 divides 18, 3 divides 36. That's the definition of divides. Another word that we've already talked about on the flip side is factor. A is a factor of B. What that means is A is a factor of B if and only if there is a whole number x. So again, I can think about a number such that A times x equals B. So 3 is a factor of 6. That's true for the exact same reason that 3 divides 6. Because I can think of a number that when I multiply it by 3, I get 6. So A divides B and A is a factor of B mean exactly the same thing. A is a divisor of B. Now, this is where you got to be careful, the difference between the word divisor and divides. A is a divisor of B if and only if there's a whole number x such that A times x is B. So we're starting to say the same thing over and over again. 3 is a divisor of 6. And again, that's true because 3 times 2 equals 6. So we've got 3 different ways to say the same thing. A divides B, A is a factor of B, A is a divisor of B. They all mean the same thing. When you do a division problem, this is the divisor, the number that you're dividing into. So, because 3 divides into 6 evenly, and you get 2, 3 is the divisor. That's where you put it, just in case you forgot about division. So now we're switching gears and we're starting with the B number. And so our vocabulary is a little different. B is a multiple of A. Well, B is a multiple of A if and only if there's a whole number x such that A times x equals B. So again, B is going to be the larger number because you're multiplying two numbers to get to B. B is going to be the larger number. 6 is a multiple of 3. This is your B, and this is your A. And it's a true statement because, same reason. A, which is 3, times 2, which is the next value that I can think of, equals B. So if you're going to use the word multiple, you've got to start with the larger number. And the same is true if you're going to use the word divisible. B is divisible by A if and only if there's a whole number x such that A times x equals B. 6 is divisible by 3 is true because 3 times 2 is 6. The larger number is B, the smaller number is A. So if you want to use the words multiple or divisible, you start with the larger number. If you want to use the divides or the divide symbol, factor or divisor, you start with the smaller number. So we're going to look at these true and false examples and try to use that information to decide whether they're true or false. So number 1, that slash, that vertical line, means divides. And this is asking, does 2 divide 10? And the answer is yes, it's true. 2 divides 10. Because 2 times 5 is 10. If I asked you to prove it, that would be proof. 3 is a factor of 12. Well, is a factor of, you can think about exactly as we did divides, it's true. Because 3 times 4 is 12. So 3 is a factor of 12. Number 3, 25 is a factor of 5. False. If you're going to use the word factor, you don't start with the larger number. 25 is not a factor of 5. It's the other way around. 5 is a factor of 25. That's the correct statement. I can't think of an integer, or a counting number, excuse me, that I could multiply by 25 and get 5. This is only true if x is a fraction. And fractions are not counting numbers or whole numbers. So there is no number, there's no whole number x that would make that true. 27 is a multiple of 2. Well, I got the big number in the right spot to use the word multiple, but it's still false. Because if I try to take 2 times x and get 27, that's not going to happen if x is a whole number. There's no whole number to make this true. Only a fractional number, 13 and a half. So no whole number makes that true. I have to say it's false. 3 divides 30. Yes, it does. 3 times 10 is 30, so 3 divides 30. 50 is divisible by 4. Well, if 50 is divisible by 4, then I should be able to think of a number x where 4 times x is 50 and x is a whole number. No, that's not true. There is no whole number to make this true. It would have to be a fraction or a decimal to make that true. So 50 is not divisible by 4. 4 does not divide into 50 evenly, in other words. That's the other way to think about it. Number 7, 3 is a multiple of 12. Well, that's backward, because if you're going to use the word multiple, you got to start with the larger number. And so we're false, because if you say 12, because this is your A and this is your B when you're using the word multiple, 12 times x equals 3, there is no whole number that makes that true. So there's no way that 3 is a multiple of 12. If you want to say it the other way around, that's fine. That's true. And last but not least, here is a question where you're using the divides and you're using prime factorization. So it's a little tricky to think about. If you get tricked, you could multiply this out and multiply that out and think about them just as counting numbers. But it is actually easier to think about it with prime factorization, because you can look at the factors of 3, and if you want to figure out if 3 squared divides into that number on the right evenly, it will if you have more factors of 3 here than you do there. So at least for this part of it, you can think about this as a 9 and this is a 27. The 9 would divide into 27 evenly. So far so good. Then you have to look at the whole thing. So now we can look at the 5 and compare it to the 5 squared. Well, the 5 would divide into 5 squared evenly, 5 into 25. So if all the factors on the left divide into the factors on the right, we're going to say true. And we'll know they divide in if we have less of them on the left than the right. So in other words, if I try to divide and I put 5 cubed here, and I put 7 to the 5th here, and I put an 11 there, I can make this a true statement as long as I have at least 5 cubed there. I can have more than that, but I have to have at least that. I have at least 7 to the 5th there. It could be more, but it's got to be at least that. And at least 11. Every factor on the left has got to occur on the right, and it's got to occur at least as many times if it's going to divide. So again, I could make this a 4, I can make this an 8, and I can make that squared, and it would still be true. But if I have 5 cubed and 7 to the 5th and 11, and on the other side of my divides, I have 5 to the 6th and 7 to the 8th, now I'm false. Because I can't make the left divide the right if I don't have at least one factor of 11 over here. So that's why prime factorization makes things easier because you can just compare each factor independently. As your numbers get really big, you don't have to be comparing the large numbers, you're just comparing each factor. And to divide, you have to have all of the factors on the right that are on the left, and at least as many times. So this particular question would be false. I'm missing an 11 on the right. So that's the material that you need to know for section 5.1. These are the definitions you need to know in order to do the Wiley Plus homework assignment, which I expect you to do over the weekend, and it will be due on Monday. We'll go over any questions you have on it on Monday, as well as the questions that you may have had. No, we didn't. We had a quiz. So no, as well as the quiz we'll go over on Monday as well. So I will see you then. Have a good weekend.